Let's proceed to the next tool in our data preprocessing, which is encoding categorical data. Why we have to do this? This data set contains one column with categories, France, Spain, or Germany. You might guess that it will be difficult for a model to compute some correlations between these columns. The features and the outcome, which is the dependent variable, and of course, we'll have to turn these strings, these categories into numbers. So one idea would be to encode France into 0, Spain into 1, and Germany into 2. However, if we do this, our future model can understand that because France is 0, Spain is 1, and Germany is 2, there is a numerical order between these three countries, and it could interpret that this order matters. It is absolutely not the case. There is not a relationship order between these three countries, so we want to avoid the model to have such an interpretation because that could cause some misinterpreted correlations between the features and the outcome which we want to predict. Therefore, we can actually do much better than just encode these three countries into 0, 1, and 2. And the thing that we can do better is actually one-hot encoding. And one-hot encoding consists of turning this country column into three columns. Why? Because there are actually three different classes in this country column, three different categories. For example, 5 countries here, you would turn this column into 5 columns. And one-hot encoding consists of creating binary vectors for each of the countries. So very simple. France would, for example, have the vector 1, 0, 0. Spain would have the vector 0, 1, 0. And Germany would have the vector 0, 0, 1. So that then there is not a numerical order between the three countries because instead of having 0, 1, and 2, we would only have zeros and ones, and therefore three new columns. What we're going to create is to replace this country column by three new columns containing the zeros and ones, encoding each of the countries. That is called one-hot encoding, and that is very useful and a popular method to use when pre-processing your data sets containing categorical variables. First thing we'll do here for this country column, remember there's this purchase column that has labels, non-numerical values with yes and no's, and we will actually have to replace them by zeros and ones. That's totally fine for the dependent variable as long as it is binary outcome. If you just replace no and yes by 0 and 1, so we'll do these two things. First, let's start by one-hot encoding the country column here. Then let's create a new code cell for this step. We're going to use two classes. The first one is the column transform, a class from the from again the scikit-learn library, and the second class is the one-hot encode from the same library. First, import these two classes, take from the scikit-learn, from which we're gonna call for us to compose module. And then from scikit-learn, once again, we're gonna get access to the pre-processing module, from which we're going to import that one-hot encoder class. And now we're going to mix these two classes in order to do this one-hot encoding on the country column. You cannot actually really guess how we're gonna do this, so let us implement the solution together. First step is to create an object of the can transform a class, and therefore we're going to create a new variable here, which I'm gonna call st, which stands for the object of the column transform a class. So ct equals You have to call the class itself a column transform a class. Since it is a class, we have to add some parentheses inside, which we have to enter two arguments. First, we will specify what kind of transformation we want to do and on which index of the column we want to transform. The second argument remain is will specify what we actually want to keep the columns that won't be applied some transformations, meaning age and salary. First one is transformers, then add a colon here, then let's just add next one, the remainder. First one, transformer, we actually have to specify three things. First, the kind of transformation, which is encoding. Second, what kind of encoding we want to do, which is one-hot encoding. And third, the indexes of the columns. We want to encode the country column. We have to actually input all that in a pair of square brackets and then some parentheses, just the format expected by this transformers argument. The first element, the kind of transformation, we have to enter here in quotes encoder. So that's the first element. The second, we have to enter the exact name of the class that will proceed to this encoding. So this is going to be exactly the second element expected here. And some parentheses because that's a class. And finally, the third element is in a pair of new bracket squares, the indexes of the columns. We want to apply one-hot encode, transform into this indexes, of course, are only one index. It is the index of the country, first column of our matrix. Remember that the Python index starts from 0. This country has an x0, and that's what we have to enter here, 0. That's all good for the first argument, transformers. The argument is equal to all this in square brackets. And now the second argument, the remainder, want to specify in quotes the following code name, which is pass-through, and which is a code name that will say that we indeed want to keep the columns that won't be applied some transformation, that won't be one hot coded, encoded, which is age and salary. Then we apply transformation on X. We will only keep the first three columns resulting from one hot encoding. We want to keep age and salary into our matrix of features. Now we have our CT object not connected yet to our matrix features X. That's exactly what we want to do. There is actually some good news. This time we don't have to do it in two steps. We're first going a fit method from the object to connect our object to the matrix of features X, then apply the second step, the transform method, to apply the transformation. This time we can do it in once because our column transform, a class, actually has a method called fit transform, which can do exactly the process of filling and transforming at once, at the same time. Use this. We have to call our city object, which we're going to call this fit transform method, which will get as input X, because that's what we want to transform. We want to transform the matrix of features X, inside which one hat encode the country column. Two things to understand. First, this fit transform method will, of course, return as input the new matrix features X with the three columns, one hat encoding the country. Since that's exactly what we want, get as the new matrix of features X, we're going to update this new matrix of features X. That's why we're adding here X equals the result of the output of this fit transform method. But then we have to do one more thing, which is related to the fact that the fit transform method actually doesn't return the output as a non-pi array. And this is absolutely compulsory to have access as a numpy array, because this will be expected by the future models which we're going to build in order to train the future models, we're going to use a train function, which is actually called fit. This train function will expect the matrix of features X as a numpy array. Here we want to force the output of this transform method to be a numpy array. To do this, we simply need to call first, which has a or name np, from which we're going to call this array function, which will take as input exactly the output of the fit transform method. We apply correctly this transformation what hat encode to the columns of this matrix of features X. Let's check that right away by creating a new code cell and then print the matrix of features X. Now let's run this cell and then running the next one. What do we see? We see what was expected, meaning that we no longer have the first country column with the text. The three countries here in strings, this time we have, as we said, three new columns. The first one, the second one, the third one, which each row encodes one of the three countries. France, that was the first row, is encoded as 1, 0, and 0, a vector of 1, 0, and 0. The Spain is encoded as a vector of 0, 0, 1, and Germany is a vector of 0, 1, 0. You see the unique idea for each of these three countries thanks to these three columns here, and that's exactly the idea of one-hot encoding. We not only turn our countries into numerical values, but also there is not a numerical order. The zeros and ones here in three columns. So that's it. That will provide the best result for our models. That's how to encode some categorical data. We're going to quickly do another encoding for the dependent variable because indeed it has a text format, no and yes. We would just like to convert these strings into 0 and 1 respectively. To do this, that's very simple. We're going to use another class called label encoder, and which will exactly encode these no's in yeses into zeros and ones respectively. Let's create a new code cell here. Encode the dependent variable. We're going to use the label encode class, which we get from the scikit-learn library. Again, we're going to call the preprocessing module, from which we're going to import the label and label encoder class. We're going to create an object to this class, which we're going to call it and we simply need to call the class label encoder, then some parentheses, and we don't have to put anything in the parentheses. We'll just need to enter directly because it is on the one single vector, which will be obvious what will be needed to encode that. First, call our object IE or LE, from which we're going to call. There is a fit transform method we can call directly on Y, and which will exactly convert the no's and yes inside numerical values. And this time we don't have to have a number array because this is a dependent variable vector. Doesn't need to be a number array, as what is expected by the model. Just set the new Y to be what is returned by the fit transform method applied to the old Y with the text no's and yes. Let's create a new code cell just to print our dependent variable vector y. Let's run this cell first and then this one. Let's see if we get zeros and ones. And indeed, we get the zeros and ones. No corresponds to 0, and then 1 corresponds to yes. It should be 0, 0, 1, 1, 0, 0, 0, 1, 1, 0. So all good. Now you not only know how to apply one hack encoding, but you have several categories in one of the features of your matrix of features. You also do a simple label encoding when you have two classes which can directly encode into 0 and 1, a binary outcome. So you have an extra tool in your data pre-processing toolkit, the way to encode a categorical data. We're going to move on to the next tool, which will be to split the data. Now you know how to handle the case where you have some categorical data in your data set, which is a situation where you will encounter many times in your career. And now we have two tools to cover. The first one being splitting the data set into the training set and test set. And the second one being feature scaling. Before we start, I'm about to enter one of the most frequently asked questions in the data science community, which is, uh, do we have to apply feature scaling before splitting the data set into the training set and uh, to set or after? So you'll find that the question in many forums in the community. Uh, some people say before and others say after. There is only one right answer, which is, by the way, after you get or which is totally obvious. So the answer is we have to apply feature scaling after splitting the data set into the training set and a test set. First, to make sure everybody understands, let's explain. Splitting the data set into the training set in a test set consists of making two separate sets. One training set where you're gonna train your model on existing observations, and one test going to evaluate the performance of your model on new observations. Understand that these new observations are exactly like some future data that you're gonna get. And we're going to deploy your machine learning model. So that's the first tool. The feature scaling simply consists of scaling all your variables or your features to make sure they all take values in the same scale. We do this to prevent one feature to dominate the other. Therefore, we would be neglected by the model. For both of these tools, let me explain why we have to apply feature scaling after splitting the dataset into the training set and test set. It is for the simple reason that the test set is supposed to be a brand new set on which you're going to evaluate your machine learning model. So it's like you're training your model on your training set, and then after it is trained, you're going to deploy it on new observations. What this means is that the test set is something you're not supposed to work with for the training, and feature scaling is a technique that will get the mean and standard deviation of your feature. In order to perform the scaling, and if we apply feature scaling before the split, then it will actually get the mean and standard deviation of all the values, including the ones in the test set. Since the test set is something you're not supposed to have, like some future data in production, applying feature scaling on the original, uh, they were said before the split would cause some what we call information leakage on the test set, would grab some information from the test set, which we're not supposed to get because it is supposed to be new data with new observations. The reason why you should not apply feature scaling before the split is to prevent information leakage on the test set. So let's implement one of the last tools of this data pre-processing toolkit, which is indeed the split of the data set into training and test set. How we're going to do this? We're going to do it with a function by scikit-learn, and it contains the module called model selection, which contains itself a function called train test split. And this function will actually do what we want, which is to create 4 separate sets. Not 2, but 4, because we will actually create a pair of matrix of features, independent variable for the training set, and another pair for independent variable for the test set. We're going to get 4 set X strand, which is a matrix of features of the training set X, or of the training set, then the X test of the test set. Y train of the dependent variable, and Y test, the dependent variable of the test. That's exactly what we want. And now, why do we want this? It's actually the model that we will build in the next part, which will be all of them expecting this format as inputs. For the training, it will expect xtrand and ytrain as input in a method actually called the fit method. And for the predictions, also called inference, these models will predict x test. It is simply the format expected by the models. And now let's get these four sets. We're gonna get them from scikit-learn, from which we're gonna get access to model selection, and then from which we're gonna import that train underscore test split function. These four variables returned by the train test split function, and as we said, they are first xtrain, the matrix of features of the training set, containing all the countries, one hat encoded ages and salaries of the training set, um, and xtrain, then xtest, the matrix of features of the test set. Then ytrain, which is the dependent variable of the training set, meaning all the purchase decisions of the customers in the training set. Ytrain, and then ytest, which same contains all the purchase decisions of the customers in the test set. So that's the four variables returned by this train test split function. It is the function that returns the variable, and let's take that function right away. Let's add here an equals and train test set. Then some parentheses. The question is, what do we have to input inside this function? There are some parentheses. This train to split or train test split is supposed to split something. So one of the inputs will be, we're about to split the data set. This function does not expect the dataset as a whole. It expects the combination of the matrix of features and the dependent variable vector y. So let's input them here. X first, a matrix of features, and y, the dependent variable vector grid. Y, then come up, and then next argument, we have to input two more arguments, which are going to be first the split size, because we're not going to split this data set into a training set and the test of the same size. We need a lot of observations in the training set and a few in the test set. But we need a lot of them in the training set to give more chance to understand and learn the correlations in the data set while training. The recommended split is to have 80% observation in the training set and 20% in the test set. Therefore, we have here going to input a new parameter, which is test size, equal to 0.2. 20% observations will go into the test. Therefore, we have 10 observations in this data set. That means that 8 observations will go into the training and 2 in the test set. It will be taken randomly. 8 of them will go into the training and 2 in the test set. We'll add another final argument. We can have the same results displayed here because we're going to run some prints to show you these 4 elements returned by this train test function. Training set in the and the test set. Some random factors that are going to happen during the split because the observations will be randomly split into training set and test. Make sure we had some same random factors. Random state equals 1. Fixing the seed here so that we'll get the same split and therefore the same training set and same test set. The code to split the data set and the training set in a test. So that's the full code. This will return indeed the four new sets composed of the training set in X train and Y train and test set in X test. So let's add a new code here to print each of these created sets. First, print X train, then going to print X test, then we're going to print Y train, and finally print Y test. Then execute everything starting from this cell, here. Done, run successfully. Then print X train, run this cell. As you can see, we have now 8 observations. This corresponds to 8 customers taken randomly from this dataset. The features here with first the 3 columns being the one hack encoded variables, the country categorical variable. We also call that dummy variables. Then we clearly have here the age as the second variable, as a second feature, and then the salary. A great matrix of features for the training set. Let's print X test. We get here 2 observations containing the same features here. This is the matrix of features still. We have the dummy variables here in the first 3 columns, then the age and the 2 salaries of our 2 customers can randomly from the data set into this test set. Then Y train, get 8 purchase decisions with the zeros and ones here. The zeros and ones here that were encoded before with label encoder. These 8 purchase decisions correspond, of course, to the 8 same customers of this matrix of features. These features can correspond to these purchase decisions. These are the same customers here. And finally, Y test, which will output to the result, meaning to the purchase decisions. One corresponding to the same customers as in the matrix features of the test. Now you have this tool, data preprocessing, splitting the data set into the training and the training set. You have this tool, and the final is we have to apply feature scaling after the split. This is to avoid information leakage because simply the test is supposed to be something you write on something on which we evaluate our model on new observations. So let's proceed to the final tool, the feature scaling, which will be applied after the split. So this is the final tool of our pre-processing toolkit, which is feature scaling. This will allow to put all our features on the same scale. Why do we need this? Because for some of the machine learning models, that's in order to avoid some features to be dominated by other features in such a way that the dominated features are not considered by the model. You also need to be aware that we don't have to apply feature scaling for all the models, just for some of them. We won't include this in our data pre-processing template, but we will show you this example. For example, in the multiple linear regression, if you have variables that take much higher values than others, when learning the coefficients will just compensate by taking small values for the variables that take high values. But for now, know that this is a tool that will be applied from time to time for certain models, not all the time. Also, in the lecture material, We want to enter one of the most important. So, how are we going to apply feature scaling? To answer this question, we're going to show you the following slide, which are the main two feature scaling techniques that indeed put all your features in the same scale. And these two techniques are first standardization, which consists of subtracting each value of your feature by the mean of all the values of the feature and then dividing by the standard deviation, which is a square root of the variance. And this will put all the values of the feature between around -3 and +3. All the different features, when you apply this transformation on all the features of your dataset, while all your features will take value between around -3 and +3. So that's standardization, and then you have normalization, which consists of subtracting each value of your feature by the minimum value of the feature and then dividing by the difference between the maximum value of the feature and the minimum value of the feature. And so since this is always larger than this. That means that all the values of your features will become between 0 and 1. So this will result in having values of features between -3 and +3 more or less. And this will result in having all the values of your features between 0 and 1. The question is also much asked by the data science community. Should we go for standardization or normalization? Normalization is recommended. When you have a normal distribution in most of your features, this will be a great feature scaling technique. In that case, standardization actually works well all the time. It will do the job all the time. Therefore, since this is a technique that will work all the time, and this is a technique that is more recommended for some specific situations where you have most of your features following a normal distribution, then our recommendation for sure is to go for standardization because indeed this will always work. You will always do some relevant feature scaling, and this will always improve the training process. So we'll show you this technique, how to apply it on our matrices of features. Matrices of features because now we have two matrices of features which are X-train and X-test. We understood in the previous lecture that, or a while ago, that feature scaling must be applied after the split. We want to apply feature scaling on the whole matrix of features X, but of course on both X-train and X-test separately, and actually the scalar will be fitted to only X-train. And then we'll transform X-test will apply for just scaling on X-test because indeed some X-test is something that we're not supposed to have during the training, but only after like when going in production. We're not allowed to fit our features on going on the test set.
Because X tests are supposed to be something new, and therefore we just get the mean of the values of X train and get the standard deviation of the values of the X train, then apply this formula to transform all the values and X trend, and then apply that same formula but with the same mean and standard deviation of the values in X train to scale the values of X test. It's really important that you understand this and to give some further elements of response to that previous question, should we scale before or after the split? So now that we are clear on this, let's proceed on the implementation of the how, meaning the implementation of feature scaling. So in order to be as much efficient as we can, we're going to do this with scikit-learn, the same library that has all the tools, and the tool that we're about to use is a class called standard scalar, in which we will exactly perform standardization on the entire matrix of features of the training set and the test set. Start by importing this class, which we have to take first from scikit-learn, sklearn, and then from which we're going to get access to the processing module that contains the standard scalar class. We're ready to import what we want, which is the standard scalar class. And now we have the class, and then the natural next step is to create an object of the class. So let's create this object. We're going to call it SC for standard scalar. And then while this object will be created as an instance of the standard scale class, adding some parentheses, and we don't have any arguments to input because what we simply want to do is get the mean, get the standard deviation, and then apply this formula to all the values in the feature. And we don't need actually any parameters. Next step, the most frequently asked question in data science is, do we have to apply feature scaling, standard deviation to the dummy variables in the matrix of features? The answer is pretty obvious. The answer is no, simply because the goal of standardization of or features scaling in general, it is to have all the values of the features in the same range. And since standardization actually transforms your feature so that they take values between more or less -3 and +3, since here our dummy variables already take values between -3 and +3 because they're equal to either 1 or 0, there is nothing extra to be done here with standardization. And standardization will only make it worse because indeed it will still transform these values between -3 and +3, but then we will totally lose the interpretation of these variables. We will lose information of which country corresponds to the observation. Remember 1, 0, and 0 corresponds to France because that's how it was encoded, and then 0, 1, 0, 0, and 1 correspond to Spain. After we apply feature scaling, if we apply it on the dummy variables, we will get nonsense numerical values, and we will be absolutely incapable to say which couple of 3 values will correspond to which country. So we will interpretation. This won't improve at all to training performance because our dummy variables are anyway already between the same scale range of the variables. Dummy variables might still increase performance, but finally will not improve. Apply only feature scaling to your numerical values. You have clearly some very different. It's better for the model that you have applied scaling, but let us leave the dummy variables out. The interpreter's ability of the model. The other very important question is to apply feature scaling to our feature matrix of features X train and X test. Then fit our scalar or standardization tool on the training set first X, and then since we won't apply feature scaling on the dummy variables, that means we will fit our scalar object only on these 2 columns here, counting the ages and the salaries. And we're gonna take 2 columns here for the age and salary. All the rows, the trick to take all the rows, you just add a column, which means you're taking the range from the lower bound to the upper bound, filling everything, and then to take the columns, this is what we have to look at. This because we want to take the column and this one, what the index says of this column. The index isn't biased and start from 0. So this has index 0. Then the second one has x1 index with age column 3. The salary column has index 4. This template as much generic as we can, and when Hack Encode your categorical variables, they always automatically go as the first column. As we want here by 3, which is the index of the age column, and then a simple column, because this will take the range from the column of next 3, which is the age up to all the other columns. There is not a -1 here. This will take all the remaining columns from the age, meaning the age and the salary. If you have a larger matrix of features, this will take just all the columns. Now, going to use our object, which we call SC, from which we're going to use that fit method that will indeed, for each feature of frame, compute the mean of the feature, meaning the mean of the age, and then the mean of the salary, and then compute the standardization of the feature, age, and the salary. And the fifth method, it will only compute the mean and the standardization of all the values. And then we have the transform method that will apply this formula, transforming each of the values here of each feature into this value resulting from this formula. So understand the difference between fit and transform. Fit, we just get the mean and standardization of each of your features, and transform will apply this formula to indeed transform your values so that they can all be in the same scale. One of the methods of the standard scale class is actually fit transform. We'll proceed to the two tools at the same time, meaning it will fit your matrix of features to get the mean and standardization. And then right after that, transform all the values of the features to turn them into this formula. So call this method and no fit underscore transform. Then sample indices. You know what to input inside this fit transform method. Exactly the same as xtrain here, because we will only apply feature scaling to our numerical variables containing non-integer values, non-dummy variables. So this will apply feature scaling to our two columns and training set. I hope you know what the next step is. Now we have also transformed our matrix of features in a test set, meaning X test this matrix of features, but this data is like new data. For this data, we will only apply the transform method because indeed the features of the test need to be scaled by the same scalar that was used on the training set. We can now get a new scalar. If we applied for a fit transfer method, X test will actually be the input of the predict function that will return two predictions after the model is trained. And since this model will be trained with a particular scalar, the scale applied on the training set, in order to make predictions that will be congruent with the way the model was trained, we need to apply the same scale that was used on the training set and the test set, so that we can get indeed the same transformation, and therefore in the end some relevant predictions will be predict method applied to X test. It's clearly the transfer method that must be applied, and therefore that we're going to do make it efficient. We're going to copy this line and we're going to place it, replace X train by X test, and then X train by X test, and then just call the transform method from that same scalar. This is part of the training. even if we haven't started the training. This operation that we apply here on our training set is the preparation of the training. So that's actually the implementation of our final tool, feature scaling, and uh, we will create here two more code cells, which we're going to print first X train and then copy this and we're going to print X test. Let's first run this, apply to scaling, no execution error, then print X train. So we have between -3 plus 3, but then our agent salary were transformed so that they take new values between -2 and +2. Sometimes you will see values between -3 and +3. Here it's -2 plus 2. But anyway, now all your variables are on the same scale, and this will be perfect to improve or optimize the training of certain models. You will see exactly which ones there are going to be the further we or as we progress in this course. So execute this cell to print X test. Once again, you'll have your dummy variables here for the same two customers that we have here. Then the agent salary will scaled so that they take once again values between -2 and +2.
Will transform access. set into training and test set.